Hi, this is Lab 2 for Physics 1. So in this lab, we're going to be talking about, or observing, how gravity affects motion of a falling object with and without drag involved. We'll cover that more with the graphs later. But we're going to cover position, acceleration, and also drag as well. And then the results of this lab: in perfect conditions, gravity causes an object that is falling to accelerate at a constant rate, but drag will make objects fall at a slightly slower rate because drag is a force that acts in like opposition to the direction of movement. So in this case, it's going down, our drag is up. And regardless of the mass, objects will fall at a constant rate, given that they have the same drag force. So some concepts we're going to cover: velocity. In this case, it's our acceleration times change in time. Our acceleration is g, 9.81 meters per second. And then for our position, our final position is equal to our initial position plus velocity times change in time. We can fill that in for this experiment. So our final position is our height minus the gravitational constant for Earth times or change in time squared. So our system is the ball, and then surroundings will be the hallway, as you'll see in the video. Our initial conditions are y velocity is equal to 0 meters per second, and every condition is 0, but we only care about the y direction. Y position is equal to 2 meters, and then our forces, we just have gravity in this case and drag, which we'll look at the effect of both in our computational data. Here's the actual experiment itself. So the curve on the left, this is the actual data that we gathered. As you can see, over time, the rate at which the position changes, or increases, becomes a lot steeper. So the velocity will change, will increase over time. And we can see this is our position versus time graph without drag versus with drag. So you can see without drag, the ball will go a further distance over 1 second than with drag, because drag is a force that counteracts the motion of travel. So possible sources of error. The video is not taken perfectly still, again. Not a perfect video to fully capture the length and movement of the ball, but also it's not a perfectly isolated system. There's wind, breeze in the hallway that's going to affect it ever so slightly, so we can't say it's a perfectly isolated system. There was some movement in the x direction, which I think ideally we should just have it drop straight down. And then according to the guidelines for the experiment, an object was supposed to have more noticeable drag, so something like a coffee filter where you can visibly see that it is slowing down. So here's some discussion questions. Velocity versus time predicted by our models with and without drag. Which of these models will actually predict a terminal velocity? So the terminal velocity will be determined by the graph that includes drag, because drag is a force that counteracts our motion. So without drag, there will be no force that will counteract the gravitational force. So without drag, an object that is basically free falling forever will keep accelerating until it hits the target or hits Earth. But with a drag force, a terminal velocity will be achieved when the drag force is equal to the gravitational force. So that means our velocity will not change, which is the next point of this question. The net force will be 0. So, and then what does it mean? It's initially thrown downward. Would the terminal velocity in this case be the same or different? So it would actually still be the same, because the drag coefficient is not changing, therefore the drag function, or the drag force, is not changing. So it'll just reach its terminal velocity faster, but the terminal velocity will not increase because it is initially faster. the terminal velocity is fixed per object and its surface area in the air.